Okay. So as we mentioned in the other room, what's happening here is that when you have a magnetic field, it can affect certain types of particles. And one of those types of particles is the hydrogen nuclei. So we're not looking at the electrons here, we're actually looking at the nuclei. The nucleus of hydrogen has this property called spin that interacts with magnetic fields. So when you put hydrogen nuclei in magnetic fields, they separate themselves into a couple energy levels, and that energy level can be probed with radio frequency radiation. Now, we're not going to get into the details of that here. The point of that is that hydrogens in different environments on a molecule will show up differently in that device, so in that presence of that magnetic field. So let's start very simply here. I've got a methane molecule. We would say that all of these hydrogens are in the same chemical environment. Do you know what I mean by that? That they're indistinguishable from each other. So if I said, everybody remember this particular hydrogen right here, and then I spun it around and did whatever, you wouldn't be able to tell me which one I'm talking about. They all look basically the same. So that's what we mean by chemically indistinguishable. What if I put another carbon full of hydrogens on there? Are those hydrogens any more distinguishable from each other, or are they still indistinguishable? They're still indistinguishable. So it becomes an issue of symmetry, right? Like this one, if I say remember that hydrogen, and then you spin it all around, you don't know which one I'm talking about, right? Okay, so let's add another carbon on here and see if we change anything. So what about now? Are any hydrogens chemically indistinguishable from others? What? The ones in the middle, right, exactly. Because if I say remember these two, or one of these two are indistinguishable from each other, but if I say remember these, it doesn't matter what I do to this, you can still pick out that those are the ones in the middle. So there become two groups of hydrogens in this molecule. The middle two, and then the outside six. That's important because when we put a molecule like this into the NMR, we're going to get one peak from that group of six, and then one peak from that group of two. So those groups are chemically distinguishable from each other. They're in different, and we would say they're in different groups, and we see different peaks for them. All right, what if we add a fourth carbon? So butane, what do you think? How many groups of hydrogens would be in there? Which two? Yeah, the middle four versus the end six. So you would get two groups of hydrogens. All right, so let's skip over some of this stuff because it starts with carbon NMR that we're not going to talk about. Let's get into hydrogen NMR. So here's a spectrum of this molecule bromoethane. So if we made a model of bromoethane, let's say this red one is bromine. How many groups of hydrogens would you expect here? Two. How would you describe the two groups? Yeah. Welcome back. So what's the difference between them? How can you describe the difference between the group of two and the group of three? Yeah.
Yeah. What is the red?
We'll say bromine, like this way.
Oh, is that right?
Yeah. Yeah, so you can say two of these hydrogens are on the same carbon as with the bromine, and then the three are one carbon away. So that's how you can distinguish them. But within each carbon, those are indistinguishable. So this group of three is all looks the same to the NMR. This group of two all looks the same to the NMR. All right, so that gives us a spectrum like this. we get two signals from the NMR, one here and one here. Now, obviously there's some more going on here because those signals are split into further little peaks. And they're pretty separate from each other. So we've talked about a couple things to understand that and what that means. The first thing is a concept called shielding. Shielding is how well the electrons on a molecule or on an atom shield the nucleus from feeling the magnetic field. So if you put this thing in this big magnetic field, this big magnet, the nucleus feels that pull of the magnet in a particular way, or feels that spin, where the spin feels that magnet. If the atom is surrounded by electrons, the electrons shield that nucleus. They don't feel that pull as strongly. As those electrons get pulled away from the nucleus, we say that it's becoming de-shielded. The shielding is going away. And it's feeling that thing stronger. So what pulls electrons away from an atom? Okay, yep, positive things. In a neutral atom, what might pull electrons away from one place to another? What are we really talking about when we say pulling electrons? Yeah, polarity in terms of molecules. So we're talking about polarity. More electronegative atoms will pull that electron away. So what we're seeing in this particular spectrum for this molecule is that the more electronegative bromine is pulling electrons off of these hydrogens that are close to it. And so those hydrogens that are closer to that bromine their signal ends up getting further to the left on the spectrum. So to sum that up, we have these kinds of, that one didn't really come out very well, but maybe it just needs to be zoomed in. No, it just doesn't really look good. Let's grab one from the book instead. So there's a table on page 387 that kind of looks like this. I'll put it up in a second. But what it's really showing is that depending on what type of environment those hydrogens are in, they can end up anywhere across this particular scale. Kind of like with IR. Remember with IR where we look at the table and determine what kind of functional group there is? NMR has the same idea, except the ranges are much bigger. So it's a little bit less useful. But where things are comparable, we can make some comparisons. So if you see, for instance, let's look at this side where we have hydrogens connected to a carbon that has a halogen on it, either I, Br, Cl, or F. You can see that depending on which halogen it is, that peak is pulled farther and farther up the scale, which is to the left on the spectrum. So we go from 3.1 to the middle threes all the way up to the fours with the very electronegative fluorine, which means that that fluorine is pulling those electrons away from the nucleus, de-shielding the nucleus, so taking the shielding away from the nucleus. There are other things that de-shield the nuclei even more, specifically aromatic rings, those rings that have alternating double bonds, have some special electrical effects going on inside them that pull those things way off. So a hydrogen connected directly to an aromatic ring is even higher on the spectrum. And then the very highest ones are connected closely with these carbon double bond oxygen groups. So a hydrogen or an OH with those carbon double bond oxygen groups, which I think you see in your spectrum. Because we know that our product from this reaction is acetyl salicylic acid. So you can look that up and see that it does have one of these groups. So that hydrogen way up to the left is the one from that group. You see that on your spectrum from today. I think everybody got a nice peak way over to the left, right? All right, so that's this idea of shielding, that we can make some conclusions about what's happening in the spectrum based on, I'll just leave that there. There. What?
What page is that?
This is 387. Now, that's not something you need to memorize, and honestly, it's not even something that's going to be all that useful when I give it to you, which I will, because there are other parts of hydrogen NMR that can tell us even more information than that, and that's what we're going to focus on now. So these two things are what make hydrogen NMR such a powerful analytical tool. The first one is the integration. That's what we did. The peaks can be integrated, and that tells you the relative number of hydrogens each peak represents. So like when we were looking at these molecules and saying, well, you know, there should be a group of 3 and a group of 2, that's going to be reflected in the spectrum. So we're going to see that this one integrates to 3 and this one integrates to 2, or a ratio of 3 to 2. And that gives us a lot of information, because then we know, okay, well, there's probably a CH3 and probably a CH2 in this molecule. And then the second thing that gives us even more information, but actually can be difficult to analyze, is what we call the splitting. Hydrogens that are next to each other, so the hydrogens on this peak versus the hydrogens on this peak, can interfere with each other's signals in a way that splits the peak into multiple little peaks. And you see that in your spectrum, and then we also see that right here. So I said each of these is a peak, but then it's split into multiple little peaks. The amount that it's split actually tells us how many neighbors those hydrogens have. And by piecing that information together, so the integration of how many hydrogens, as well as the splitting, you know how many hydrogens there are in a group and how many hydrogens there are next to the group. And that usually gives you enough information to determine the whole structure. Not always, but often gives you information where you can actually write the whole structure just based on the spectrum. So let's talk about that splitting and what that means. The first thing about the splitting is we have this n+1 rule, which means that you're always going to get one more peak than you have hydrogens splitting the other hydrogens. So if you have a triplet, meaning a set of 3, so we have one of those here. This is called a triplet. You can see 3 peaks, right? 1, 2, 3. Your question? Yeah. This is in the notes, by the way, also. So I'm just kind of using this as an example. It's in that folder online. So while we're here, that splitting with some exceptions, and then depending on the instrument, even more exceptions, but generally for our purposes, the splitting is going to occur between 3 bond neighbors. So if you have a hydrogen, that's 1, 2, 3 bonds to the other hydrogen. 1, 2, 3. So that's another way of saying hydrogens on adjacent carbons, or neighboring hydrogens. That means we don't get splitting from 2 carbons over, from 3 carbons over, generally in these types of spectrum. And similarly, the hydrogens on the same carbon will usually not split each other because they're usually not distinguishable by the NMR. They're usually in that same chemical group. And then how you tell that there is this kind of splitting and it's not just a couple peaks that happen to be in the same place as each other is this idea of coupling constant. Now we don't need to get into all that here, but you can see that the spacing between the peaks is roughly the same, and they have a nice symmetrical lineup. So it's like a triplet looks like short, tall, short. You see that on the right? Not exact, but pretty much short, tall, short. And then the one on the left is what we would call a quartet. It's 4 peaks. It kind of goes short, tall, tall, short. So you have that nice pattern that kind of looks like a peak within itself, right? If you were to draw something like that. That tells you that this is that special kind of splitting, not just some peaks that happen to be really close to each other. Okay, so let's put all that together. What does that mean? So this peak has 4 splits to it. It's a quartet, which tells us that this particular group, whatever that corresponds to, has 3 neighboring hydrogens. So it's not a group of 3, but that group has 3 next to it.
And why was that again?
Because it's split into 4 peaks. It's a quartet. And we always split into one more than the number of the neighbors.
And the other one's 2.
So that's right. So this one, that means that this group, whatever this one is going to be, has 2.
So that doesn't mean they're
Neighbor.
attached to it, it means they're attached to whatever's adjacent to it.
Right. Yeah. And then what we're not told on this particular spectrum is the integration. So how many are actually in there? What we would expect to see if we integrated this, like we did with your spectrum, we'd get that little thingy. I'll use a different color so we don't get lost here. The green never seems to show up that well. So we get that little integration symbol. And so this one would say 2.00, and this one would say 3.00, or something about around there. They're not always even numbers experimentally. You round up or you round down, depending on what makes sense. Yeah, it probably rounds up to 3. It depends, because it's an arbitrary thing, because we picked where to start and stop there. So we're not always picking in the exact right place or in the exact same place, and that's what gives it that variation. All right, so with the integrations, now we can have a full picture of the spectrum of this molecule. So the 2 hydrogens from here are split by these 3 hydrogens next to it. All right? So this is the group of those hydrogens, the ones next to the bromine. And then that is the group of 3 on the other carbon.
Where does the bromine go?
This is hydrogen NMR, so we're only looking at hydrogen atoms. We're not looking at carbons, we're not looking at bromine or anything else. We only see signals from the hydrogen atoms. The other thing we can tell here, or the other way that we can confirm that that's correct, that our assignment is correct, is that the 2 hydrogen group is shifted further to the left, further down, that's called downfield, the higher numbers, which means that those hydrogens are more de-shielded. Those electrons are being pulled more away from the nucleus than the others. And that makes sense because those are the ones that are closest to that bromine, and the bromine is doing that pulling. So the ones closer to that bromine are going to be, the hydrogen nuclei are going to be more exposed to the magnetic field, more pulled away. All right, let's look at some other spectra and see how they look similar. Yep.
Okay, this is neighboring hydrogens. How is that 2? Wasn't it supposed to be switched?
So this is a group of 2 hydrogens that has 3 next to it.
Oh.
And that gets confusing. That's exactly what is often confusing. The peak itself is caused by those 2 hydrogens, and that's why it integrates to 2. What?
So they tell each other.
Right. So they kind of tell each other. But the splitting pattern tells you what's next to it.
Oh,
So the integration tells you how many are in that group. The splitting tells you how many are next to that group.
so it would be like whatever's next to that H2 would be what that peak
Right.
is.
Yep.
Okay.
Right. So let's look at how that compares to this one. This is now a 2-bromopropane. What we see here, although again, for some reason it didn't come out quite right,
I just look like a blob.
it just looks like blobs. Let's skip this one, see if we have a better looking one. Here, this one's a little nicer looking. I'm going to turn oh, you can't see it on the screen though. I'm going to turn the lights down so maybe we can see it.
Can you see that? Like,
Can you see it at all?
No.
No, it's not showing up at all. It looks great on this screen. Let me outline it for you.
it's so artistic.
Thanks, I guess.
Honestly.
I didn't know like tracing over other lines was a form of art, but yeah, I guess I'm good at that. Okay. Did I get them all? Yeah. All right, can you see that okay? Can you turn the lights back on? All right, so that's what this one looks like. This is this one bromopropane. Let's look just at the splitting pattern and the shield and the deshielding, the shift, called the chemical shift, and see if we can figure this out without even looking at the integrations. So the integrations often are our best clue to what this is, but we're gonna leave the integrations off here for now. So what can you tell me about any of those peaks, anything that you see at all?
The first one and second one, they start off down, up, and down. So it's like triple, so it has two neighboring.
Yeah, so that one, when you say the first one, you mean the one on the left?
Yeah, the one on the left and on the
The one on the left and the one on the right are both what we would call triplets, meaning that those, whatever those are, those groups are, they each have two neighboring hydrogens. What about the one in the middle?
That would have 5 neighboring.
Yeah, that's what we call a sextuplet, right? 6 peaks, a sextuplet, 6 peaks. Doesn't matter. Anyway, there's 6 of them. So that means that it has 5 neighbors. So which group of hydrogens in that structure has 5 neighbors? 5 neighboring hydrogens. None of them have 5 neighboring hydrogens?
Like together, close.
They don't have to be together.
I mean, like together, there's 3 in there.
The first carbon after this one?
The next one.
This one. Yeah. So these 2 hydrogens have 5 neighbors, 3 on this side and 2 on this side. You see that? So that means that those hydrogens must be represented by this peak. Right? What?
Okay, I get that.
Okay.
But when you go to the peak all on the left,
Mm-hmm.
by 4 or 3, you need one where it has, where the adjacent is 2.
Right. So each of these has 2 adjacent, which is this one. So this one has 2 adjacent, and this one has 2 adjacent. So which one do you think is which? It does.
Isn't the higher one H3?
The one with the higher one is going to be CH3, so yes. How else can we know that? If we didn't have that kind of... The what? Yeah, the deshielding, the electron pull. How is that going to present itself here? Right, so the ones closer to the bromine are going to be pushed to the left, to the higher numbers, leaving the ones further from the bromine over on the right. So that tells us that this group is represented by this peak, and then this group is represented by that peak. All right, so that's how we can interpret these kinds of things. But the real power of this is going to be using a spectrum to completely figure out an unknown structure. So let's see if we can do that. Oh, I don't have any. Okay. I thought I had more pages. They must be in a different file. I'll find them. These are getting a little... All right, we'll come back to this. Let's look at some in the book here to start with. So the types of problems that you're going to see from this look like this. So this is 11.35. Problem 11.35 on page 405. if you want to follow along. Whoop, that's all kind of crooked here. It says, if you can read that, the following is a hydrogen NMR spectrum for compound J with molecular formula C7H14. Compound J decolorizes a solution of bromine in carbon tetrachloride solvent. What does it mean to decolorize a solution of bromine? What does that tell us about it? Ideas? That means it reacts with bromine, with Br2. What kinds of things react with Br2? No, organic compounds. So this is only carbon and hydrogen. What kind of organic compounds react with bromine? Here, I'll do that on the board. If you had some kind of compound that reacts with bromine in carbon tetrachloride solvent, what kind of a compound is that? Like what kind of a functional group reacts with bromine? Nobody remembers?
I'm staring at you for the answer.
I'm staring at you for the answer. Do alkyl halides react with bromine? Do you react with bromide, maybe? Bromide, but not bromine. Do alkanes react with bromine?
Yeah.
Nope. Do alkenes react with bromine? Somebody's going to get one of these, right?
Yep.
Alkenes, right? So things with double bonds, right, react with bromine to make these kinds of things. You got to remember all these reactions from these chapters. These are not isolated chapters, right? All this stuff comes together.
You can't just put the middle step in and ask the first step.
I didn't mean, yeah, I said what kind. So any kind of alkenes. That was just an example. So the information we get from this is not the right structure, but the information we get from this is that this, well, here, now that we've, this C7H14 structure reacts with bromine. Which tells you that it has an alkene in it. It has some kind of double bond. Or I suppose a triple bond, but you couldn't have a triple bond with, what am I trying to say there? You couldn't have a triple bond with only C7H14. There's not too many hydrogens. Okay, so we've got to piece this thing together. Now we know that there are a lot of different ways that we can draw a structure for C7H14. There are many different isomers of that, right? And we could draw some. So you could have your double bond over here. Okay, you can have it branched somehow. The double bond. There are tons of isomers of possibilities. There are many, many possibilities. Yeah. This is just telling us that we have to put a double bond in there. That's what this tells us. So we can use the NMR to determine how we're going to design this structure. Because there's so many different isomers, we can't just figure it out by drawing isomers. We use the NMR. All right. So what does that NMR tell us? We've got, can you all see that okay, or do you have it in front of you? I'm going to redraw it actually on the screen so we can have it for review purposes. Okay, so here's my baseline. There's nothing above 5, so I'm just going to start at 5. And right at 1, there's a really big singlet. With 9 hydrogen integration. And I'm going to put an S for singlet, just so we don't always have to draw the little splitting. We could say, look, that's a singlet for 9 hydrogens. Then just before 2, there's a smaller singlet. Singlet meaning just one peak. Right. And here's a singlet with 3 hydrogens. So how many neighbors do each of those have? No. Remember, we get the neighbors from the splitting. So these are not split at all, which means that they have no neighbors. Right. So when it's split into little parts, that tells us the neighbors. That 9 hydrogens, that's the integration. That tells us that particular group has 9 hydrogens. Okay. Yeah. Okay, so then we've got a 3 hydrogen group that also has no neighbors. And then way over here at between 4 and 5, we have 2 little doublets. So doublets meaning like that. Like that. Oops. Same place. This is, I'm just redrawing the one in the book here. Yeah, so this is on page 405, the bottom question, 11.35. So this is a 1 hydrogen doublet, and this is a 1 hydrogen doublet. And the formula here is C7H14. So all we know is that it has a double bond. It has 7 carbons and 14 hydrogens. And those are the groups that they are in. Now we have to figure out the structure. Yeah.
The doublet has 1 hydrogen splitting? Like one.
The doublet has,
One
yeah, so that means that it's 1 hydrogen and 1 neighboring hydrogen. The 1H tells us that that group is 1 hydrogen. The doublet tells us that there's also 1 next to it.
So that's splitting, right?
Yeah, that's the splitting. Yeah, and in the book they say closely spaced doublet, just because you can't actually see that it's split. So it's telling you it's a doublet in the book. We're going to do the same thing. Okay, so the way to think through a problem like this, the best strategy for this is to find pieces, almost like puzzle pieces, and then put them together, rather than just starting from nothing and kind of working your way, feeling your way through in the dark. We should be able to find some parts that we can then stick together to make sense of this. Maybe, if we're lucky. So the thing that first sticks out at me here is that big 9 hydrogen singlet. There is no CH9, right? You can't have 9 hydrogens on a carbon. So what does it mean to have 9 hydrogens all in the same group? What does that tell you about the type of thing that could be there? Well, we know there's a double bond. How does that help us get a group of 9 hydrogens?
Isn't it 3 groups?
Yeah, it's going to be 3 groups of like 3 CH3s that are all equivalent, right? That you could mix them all around and you couldn't distinguish them. So what might it look like to have 3 groups of 3 that are indistinguishable on a chemical structure? Yeah, like a chicken feet kind of thing. We can look at the model of that too. Here. So since we know that we know CH3 is a pretty common group. So it's a reasonable guess to say, well, if it's 9, that's probably 3 CH3s, right? If it were a group of 6, we could say, well, that's probably either 2 CH3s or 3 CH2s, because those are commonals. Again, there's some trial and error here. So we can make some guesses and then check our guesses and see if they make sense or not. All right, so let's say I take 3 CH3s and stick them to another carbon. I got too many here. Oh, too many things. So there's a CH3. There's one. And here's one more. All right, so there's 3 CH3s stuck to a center carbon. Is that what you're talking about? There's your foot or whatever. Yeah. Because if you took any one of these hydrogens, they're not distinguishable from any of these other ones. They're all equivalent looking. So let's say that's possibly one of our pieces in this molecule, one of our pieces that we're going to be able to put together. That's going to look like this. And then that's going to be our connection point where we can connect to something else. So that might be this. Notice I'm using words like might because there's guessing involved here. You have to guess what these things might be, try to put them together, and then go back and see if they fit the spectrum. If they do, you're right. If they don't, then you got to go back and question your previous assumptions. All right, so we've got that. What do you think this 3-hydrogen singlet is? What kind of a group is going to give you a 3-hydrogen? Yeah, a CH3. So probably over here, another piece that we have is a CH3. So can we just put those two together and we've got our molecule? No, why not? Yeah, first of all, we don't have enough carbons and hydrogens here. And we also know that we need something else here that we haven't dealt with. Right, so one thing we can look at is this chemical shift. We see that those doublets are between 4 and 5. And if we look at one of those tables, we'll see that things that show up between 4 or 5 are hydrogens that are on double bonded carbons. So that might be what our double bond is. If we had 2 double bonded carbons like that, those two could split each other. And then that might give us these, right? They're each 1 hydrogen, and then they have 1 neighbor as well. Okay. So how are we doing now on our atom inventory? Have we accounted for 7 hydrogens or 7 carbons and 14 hydrogens? We have, I think. So that means we've probably found all the pieces. And there's only one way to put them together. You see that? If we need all 3 of those pieces, there's only one way to stick those pieces together. You just have to connect them. Because they only leave us with particular connections.
Wait, so the CH connected to the methyl group?
Yeah, right. So we put all this stuff together and we end up with this, and then connecting to the double bond. And then that's CH3. So I may have looked at this wrong. I can't really tell. But if that's the case, that this maybe is supposed to be a doublet because it should be split by that one as well. But anyway, that's the only choice we have. That's the only way to connect those pieces together. So if you look at the spectrum and you find these pieces, then you can connect those pieces together to find the overall structure. So now we know that this is the correct structure. That is that C7H14 with the double bond that they're talking about. One thing we don't know if the double bond is E or Z. We can't get that information from just this. There are ways to get that from NMR, but they don't really tell us here. So we would say that either of those could be correct. Okay, let me pull up this other thing that I had. Save it in the notes here.
All this online?
Yes. We'll do some of these together, and then I'll let you do some of them as well. So sometimes, like in these examples, you don't even get the spectrum, you get just some data. I will try to stay away from those when I give you some examples, but these examples are really not that good. Okay, let's look at this one together. So here's another interesting example, and this is something that you'll see on the next exam. You could be given multiple types of spectrum, like an IR and an NMR. With just those pieces of data and the chemical formula, we should be able to figure out exactly the structure of this molecule. And this is a big molecule. I don't know if you see that down there, C10H13 or C10H12O2. So this is a big molecule. But we're going to use the same technique to work through it. We're going to find these different pieces. We're going to put the pieces together and then check and see if those pieces make sense with this spectrum. So let's look at the IR first, because that actually gives us less information. So it's quicker. What do you see in the IR up here? Anybody get any information from that without looking at a table? What?
I'm just saying you stress me out.
Okay, they stress you out?
Yeah.
The what? The OH stretching. I would say probably not in this one. That's usually higher, like 3,500. We would expect to see a much bigger peak for OH, because that's a strong one. Right, so that first time, we first look around 3,000, right? And we see that there is stretching both below and above 3,000. So that's going to tell us this molecule has probably carbon-carbon single bonds and double bonds in it. What else do you see here? The peaks up here? What does that tell you? Yep, this is generally a signal of a benzene ring, that aromatic ring. But also there can be some other stuff there, so I'll hold off on saying for sure until we look at something else. What about this big strong peak at 1,700? What does that usually tell us? You remember? You will have those correlation tables on the exam. Yeah, it can be any kind of carbon double bond oxygen. So carbon double bond oxygens always come up between, let's say, 1,600 and 1,800. It's really the only thing that's in that area. So then between this and then some of these other peaks over here, we'll say a benzene ring with a question mark. Maybe? A good guess for now? We'll see if we can confirm that. So this, just to recap here, this tells us that we have sp3 carbon hydrogen and sp2 carbon hydrogen going on here. All right, so that's all the information we get from the IR. Remember, IR is not that useful. It tells you some of the functional groups. Sometimes it doesn't because it's confused with other ones. It doesn't give you that much information. But it gave us some. So now we can move on and look at the NMR. The one thing that I want you to always look for in your NMRs when you're trying to analyze this are peaks between 7 and 8, or let's say 6.5 to 8. Let's say 6 and 8. There's really only one thing that's in that region. Does anybody have a correlation chart open? Can take a quick look at it. I can show you in the book here. Let's pull this table back up. Whoops. I said between 6 and 8. So between 6 and 8, really the only thing that shows up there is right here. Oh, the IR chart. Yeah, no, we're looking at the NMR now. So the only thing between like 6.5, 8.5, or 6 and 8 is this ARH. And when we see AR, that stands for aromatic. That tells us those benzene rings. So our suspicion from that IR is correct. There is the NMR confirms that there is absolutely, so let me show you again on the spectrum. There is absolutely benzene ring here. But because this is NMR, we get more information about that benzene ring. The more information we get is from the integration. Can you guys read that number? Can you all read that number? It's 4. So what does it tell us that the aromatic hydrogens, the hydrogens on that benzene ring, integrate to 4?
Wait, why is it 4?
It's telling us that that all is one group together of 4. We'll talk about why that is. Yeah, so it tells us that there are 4 hydrogens from this ring. Now, this ring has 6 carbons on it. So if there are 4 hydrogens, what does that tell us about the other 2 carbons? Yeah, exactly. Those carbons are attached to other stuff. So we can come up with another piece here as being something like this. Right? 4 hydrogens, 1, 2, 3, 4, and then 2 connection sites, 2 spots that can go on and connect to other stuff. Now, the other thing you need to know about that aromatic region in the NMR, those special types of rings, those aromatic rings with alternating double bonds, which actually we will get into a little bit in the next chapter, those cause all kinds of unusual behavior in the NMR. They cause the hydrogens to be able to split beyond 3 bonds. They can actually split across the ring and all kinds of stuff. So often that region will be a mess. It'll have a bunch of different little peaks there. And I think that's what you see in your spectra from today, right? If you look at that spectrum, in that aromatic region, in that region from 6 to 8, where we see those rings, you just see a bunch of junk.
Yeah.
And so what that tells us is that the word for that is a multiplet. We don't really know if it's a doublet or a triplet or a quartet. We can't really analyze that splitting. It's just messy. It's all on top of each other. So we just say that's the aromatic region. That's the splitting from the aromatic region. And we can't really get more detail than that. So we can't really talk about how many neighbors it has because it's just too messy. So all of those are going to, that's why they lump all this in as one with 4 hydrogens also.
So whatever number is on top.
Yeah.
I don't know if that's how many hydrogens.
Yeah, so I think you've all got 4 also, right? Like one and then 3 that are in that region. So you'd expect, yeah. So you'd expect 4 hydrogens. So if you've got an aromatic region with 4 hydrogens, that tells you it's got to have 2 connections because 4 hydrogens leaves 2 to make 6 carbons. If you had one with 5, then you'd have just 1 connection, and so on. All right, so we found one piece. We found one piece. Let's start looking for some other pieces. What other pieces? It does, but we're not really going to get into that. So if you have this nice doublet like that, that nice splitting, that usually means that they're across from each other. And if it's messier, it means they're not across from each other, either right next to each other or one away. If you go on and take more organic chemistry, you'll get into how you figure that out. We won't do that in this class. So, all right, so let's just look at the other peaks now and see what other types of groups we can find. So what kind of groups do you see in these other peaks in the spectrum? What? The one over by 4. So that's a group of 2. So what kind of a part is that? What kind of a piece do you think that would be? This one has 2 hydrogens in it. So that's probably what? A CH2. And we know that a CH2 connects on 2 sides, right? Needs 2 more bonds. So that gives us one more piece. Similarly, we might say that this is probably a CH2. And this one is probably a CH3, which has one connection. There's one more piece that's actually off the scale, so they had to draw it a little bit separately. A 1 hydrogen peak way up at 9.8. This is where you might look at the correlation table. And there's really only one type of a thing that comes in at 9.8. And that is down here, an aldehyde. So a carbon double bond oxygen with a hydrogen next to it is in that range. And it's really the only thing that's in that range. So because of that, we can say with pretty good certainty that this peak over here is probably a C double bond O with an H, and that gives another connection. All right, so now we have some choices to make, because we have a lot of different groups that are connected on multiple sides. We have two end groups, so two groups that cap ends, the CH3 and the aldehyde, the C, this thing, this is called an aldehyde. We can't just stick those two together, because then there wouldn't be anything in the middle, right? That would be our whole molecule. So we have to put those things on the ends, and then we have to figure out how to put all these other little pieces in the middle. Any idea how we're going to do that? Yeah, we got to stick all these things together. So how do we determine the combinations? Yeah, what were you going to say?
Well, can like the carbon and the hydrogen have like the double bond and the oxygen and one of the pieces?
Yes, so that'll go onto one of the pieces, but where? Which piece? How do we know which piece it's going to go on?
It goes on the ring.
It goes on the ring?
So does it matter which side?
No, but how do you know it goes on the ring and not onto a CH2 and then onto the ring or something? So it's not splitting? Right. Right. So I'm kind of running out of space here. So we know that, let's turn it around just so we have room. So we know that that's likely to connect to that ring. So now we can make that piece. All right. Let's look at the other side now. We've got two CH2s and a CH3. We need to know if we have to connect them all together or if we have to put something else in there. How can the splitting help us to determine that? Yep. Yep. Right. So just like we saw in that example, that CH2 right here, it's actually got 6 splits, which tells us there are 5 neighbors. So 5 neighbors means it has to be in between a CH3 and a CH2. And we've got a CH3 and a CH2. So that means that we can combine all of those and say that we're going to have a piece that looks like this. But when we say that, we also want to check that it makes sense with the other peaks. So that means that this CH2 should be split into how many peaks? How many neighbors do these hydrogens have? Just these two. These two have 5. These two have 2 neighbors. So that means it should be split into a triplet, 3 peaks. And then these also have 2 neighbors, so they should also be a triplet. And that's exactly what we see, right? That one's a triplet and that one's a triplet. So that tells us that we can be reasonably certain that this is another piece. So now we've got this piece and we've got this piece. Can we just stick those two together and we've got our answer? Maybe. We got one little problem. We're super close. So let's stick those two together and then look at what our problem might be. That looks good, and that fits all of our splitting. There's one little problem. Anybody see it?
We have a question.
Yeah.
Isn't there more than 10 carbons?
Well, let's check that. That's always a good thing. So we're supposed to have 10 carbons, 12 hydrogens, and 2 oxygens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 10 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got 12 hydrogens. Only 1 oxygen. So where can we stick another oxygen in that doesn't mess up all of our splitting and all of our other stuff that we've been doing? Well, we also can't have carbon with extra bonds. So where can we stick an oxygen that doesn't mess everything up?
On the CH
Here, like that. That's too many bonds on that carbon. So that would be a possibility. Why doesn't that work though? Yeah, because then we'd see that big broad peak from the carboxylic acid in the IR, and we don't see an OH in the IR. So where can we put an O that doesn't make an OH and that doesn't mess up anything else? Yeah.
Can you put the aromatic ring?
Like this?
Yeah.
What's wrong with that? It messes up our peaks because we need 4 hydrogens on the aromatic ring. And also oxygen needs 2 bonds. Yeah, so that's where it goes without messing things up. We can put it here. See that? In between those two, make an ether type functional group. That doesn't mess up any splitting. Doesn't change any double bonds. Here, maybe we should stretch this out a little bit so we can see it. That's the only place we could really put it in. The other place would be in between this carbon and these two here. There's a reason that doesn't work, but for our purposes, that would be fine as well. So we can put it in between these bonds. And that doesn't change anything. So that is a good, correct final structure.
Wait, where did the second oxygen come from?
Because in our formula, we know we needed 2 oxygens. We were given the formula and it said you have to have 2 oxygens. All right, now let's do the same idea with your experimental spectrum. You have the structure for your experimental spectrum, right? You know what the structure is supposed to be.
Yeah, which I'm confused about.
Yeah, from the pre-lab. So what's the product supposed to be? And then work with your partner or whoever and see if you can assign the peaks. So which hydrogens from the structure should correspond to which peaks on the spectrum? Actually, it will. Even though it looks a little weird, it should still work. The only thing that's messed up here is the integration between the off. So you've got to do 3, 4, even though those numbers aren't necessarily close to that, that's what they should be. Knowing that, you should be able to assign it.
No, I just.
Yeah.
It would be like a double peak and then this.
Actually, this one should be a single one. Yeah, I don't know why that has that. Probably
That same row. And then
that is just a mess. Yeah.
So we can't go off.
You won't be able to assign all the splitting in this one because there's just too much mess in that region. but you should be able to do it in the integrations.
This is what I meant, but
Yeah.
is that it?
Yeah.
We need to add.
That's CH3.
Yep.
Which one?
Yep.
And, yeah.
Correct.
I won't give you sure.
But that doesn't account for the entire formula of the structure.
We need to add those.
But yeah, it's just
Or
around.
just,
This is your formula of the structure. That's the problem.
Right, so
So-
I have everything except.
Yeah, so instead of a CH3 directly connected to the ring, it should be a CH3 connected to this.
Okay, but then I don't have it happening that. The system.
No, that's, right. So these parts won't show up in the NMR because we're not that. So that's the part.
But that, yeah.
But that's CH3. Yeah.
These, so you have to use.
All right, I'm gonna grab another practice sheet. I'll be right back.
This one. 8.
Don't do that. Stop it, so. Yeah. So they won't be able to go off the actual piece, it's the same piece. Weird, but. Or one thing, yeah. No, that's a part. Oh, and that's C. Yeah, sorry. COOH. COCOH. Oh, okay. Oh, yeah, sorry.
When they tell you to look at it from this number, you can't on the bottom like this.
I was misreading mine over here. I thought it was 4. I just clicked yeah, that's how I saw it right there. Yeah, I was misreading. I just oh.
Yeah.
That would be.
So, I was. I'll type this.
Wait, what is this?
Yeah. Because look, it starts right at 2 and it ends right at 4 with the. I'd rather have the 1. So it could be either one of those.
But like, we see. There's a lady coming out. You mean it has to go this whole range? Oh, it doesn't just have to fall in the middle, it has to be that. So if it was this, I thought it fell, it has to be 1.6.
Yeah, that's close.
So maybe it's not this then, this doesn't look. So this could only be, yeah, that's just what I'm.
Yeah.
Yeah.
Yes.
Okay. Does it fall in between these? Or does it have to be?
Generally, but just like with IR, those are kind of rough guidelines, so if you need something to not be in there, then
Mhm.
And that's exactly.
Right.
so that's not good. You can't use this the way you use it in IR, where you say, oh, that fits in here, so it must be this kind of thing. Because there are a lot of things that are different.
So what could be this
So it can be this, it can be this, it can be this, it can be that, you know, it could be any number of things, which is a huge, it could be stuff that's not even on here, it could be this, it could be that. The point is, you know the structure, you know what the structure is, right? You have it written down somewhere. So you should be able to assign the teams based on what you know the structure. No, because it can be anything that has something. That's right, but that doesn't necessarily mean that your carbon is connected directly to it. Right?
What about everything?
Nope, you don't even really use this except for sort of a general, try to find those pieces and let the pieces are. That's a better way to do it. So looking at the spectrum, say, okay, this is a 3-hydrogen group, so that means a CH3. So what might that CH3 then connect to? Right. So when you get the 3 or so different parts, then you can put those pieces together and see how they fit.
Okay, so for this.
Yeah.
I got 7 neighboring by 4.
Right. So as I said, in an aromatic region like that, you can't calculate the neighbors because the split is not clear enough. So everything's all split. So you have to just, all you can get to this information is that it's an aromatic group with 4 hydrogens. So that's one of your pieces. An aromatic ring with 4 hydrogens on it, which means it's connecting to 2 spots. So 2 of the carbons don't have benzene ring. Well, the benzene ring has 6 carbons. So if there's 4 hydrogens, that means there's 2 spots left to connect to other side.
Okay, and there's a follow that's like
Well, there's maybe 1 attached to each carbon.
okay, that's it. That's what and then there's 2 spots for each side.
Right. So then you find the other things.
And how do you think that?
The other things that you find in your spectrum, in your product.
Use it based on the use.
Well, you use it where it's necessary, where, especially in the low end of like down here, there are just so many things that can be there that this chart is not so helpful. On the high end, it is. So, for instance, you have one that's up here close to 11, and you'll notice there's nothing. There's only one thing that could possibly be that high, which is a carboxylic acid. So you know pretty good certainty what that is. But down in that 2 range, there's so many different things that can be that chart is not useful.
Like,
Right, same thing. There's only aromatic stuff in that range.
okay, I have a question.
Yeah.
You have to split that.
Well, we split it, but really it's all kind of in the same range. So when you look at your structure, you may be able to see, hey, this one hydrogen could be closer than this other, but probably not. So it's your 4 hydrogens.
Right, I'm gonna focus on the sheet. So were you able to find some of those pieces from the lab structure? Well, look at the structure. You don't have to do it blind.
Because we know the structure.
So we're trying to figure out.
Yeah, so which part goes where?
Okay, so this part was right here.
Yeah, that's the high, remember, these peaks are only caused by hydrogen. So non-hydrogen atoms won't show up here. So that peak specifically refers to that hydrogen atom right
Is this specifically our method?
there. Yeah, that's what I was.
Oh, I think this.
No,
And then this is the method,
Right. so that's your 4 hydrogens.
That works.
Right there.
And then we determine what is actually.
Right, but you won't see the carbon or the oxygens. So you only see the hydrogens connected to that carbon on the end. So how many hydrogens are on this carbon over here? 3. So that's going to be, where do you see that in the spectrum? Not on the table, in the spectrum. Where is there a peak of 3? Yeah. So that's
Oh,
a peak of 3 hydrogens.
four?
Yeah.
What is supposed to be hydrogen?
Yeah.
Oh.
And that actually is on the table here, right here. That's 3 hydrogens on a carbon. It's next to a carbon, double bond oxygen. 2.1, 2.3, so that's what we see right here.
So that would be.
Right? Carbon, 3 hydrogens, and then carbon double bond.
This is probably on the top.
Yeah.
So like this one.
So let's go through some of these other practice ones then, if you've gotten this one all right.
Yes, yes.
Yeah. So how's this going?
Okay, so
That
that means that
Mhm.
this one.
Although in that case, this might be another something weird happening here, because everybody else's goes way higher. So, because if you look at your structure
We're
here,
missing one.
it should
We
really
can't
be an
get-
OH.
Well, yeah, because that's what we're trying to.
Yeah, so this should be the OH, that should be
So
this.
for the single peak,
Right.
and then there'd
It's
be
just too
one
low for some
more,
reason.
would there be
No, well,
one?
this peak should be over here. I don't know why it ends up low.
Okay, so then the question is where would the double show up? Or is this?
It does, because we're only looking at hydrogen atoms.
Oh, okay,
So
so
we don't
then,
see anything else.
so then this would be, that right?
It would be, yeah, it would be these hydrogens over here. Well, this is 3. CHM. No more.
Not
Yeah, it's there. Yeah, you want to look at the
so it's
actual.
this one, double bond CH3 now.
But there's another carbon. So it's C double bond O and then a carbon. Sure there is. But again, it doesn't, the table is just a selection of things that could be in there. It's, yeah.
Okay, so and then that's what you want us to. We're gonna show on.
Yeah, draw the structure and then you could do it the way you did, or you can just draw arrows that says this part of the structure goes to this part of the structure. It says this part of the structure.
Wait, I have a question. You told us to write this as 3, right? Would you show us again on the test and give us that number?
Yeah.
That makes sense. Thank you.
So what you really, when you do an unknown compound, what you can do is you'll set the smallest peak to 1, and then it'll do the multiplication. So like if you have 1 and then another peak shows up at 1.5, well, you can't have half a hydrogen. So that really means that that should be 2 to 3. That. So that's the way to do it if you really have no idea what it
Smallest
is.
peak, you mean like the smallest or the shortest?
In the spectrum, yeah.
Okay.
So if you really have no idea, that's kind of how you would guess it, but on something like an exam, I would give you the integration values.
What's known at?
9. That means it has 9 little splits. So yeah, once you get a sense of that, move on to this next sheet and see if you can start piecing these together from their formulas and their and the peaks.
What's known at?
That means 9. There's 9 little peaks there. Double it. That's 2. So sometimes they don't, for some reason they didn't print super well. The lines were too fine or something. So you don't always see them all.
So, we have this thing.
Yeah, T is triplet. Yeah, so I would look at the numbers first, the integration numbers, and then the splitting to help you piece it together. Because the numbers will tell you how many are in that group. The splitting tells you how to put the groups together so that the right things are next to each other. Yeah.
What else?
General life question.
I'm like trying to get this.
So again, start writing down some of those pieces that there might be. All right, don't even worry about.
Like 12.
That's right. So don't even worry about it yet. You should be able to write down these different pieces, and then we'll figure out how to piece them together. All right. After you, so yeah. So you've got a group here that has 2 hydrogens.
The problem is this.
Don't worry about the group. What's that?
Yeah, close the book.
Yeah.
Close the book.
The 2 hydrogens are probably CH2s. Right? I mean, likely a group of 2 hydrogens that are the same is going to be a CH2. It could be 2 CHs that just happen to be exactly in the right position, but likely it's going to be a CH2. So you have one piece that's a CH2 that has 2 connections. Because the CH2 has 2 connections, so that's one piece.
Isn't this, what is this hydrogen mean?
Well, yeah, but there's not enough carbons, right? Because we only have 4 carbons.
And this one takes up one.
Yeah. So what's another way you could have 6 hydrogens?
Oh, the CCC. C, like, 2 CH2s.
You could have 3 CH2s, but that again would be difficult because they'd all have to be exactly symmetrically the same. There's an even better choice than that. Yeah, 2 CH3s. So a group of 6 could be 2 CH3s connected to 1 carbon, then those would be indistinguishable from each other. Not connected to each other, because that doesn't allow you to connect to anything else.
There's 2 of them.
Yeah. But the way you have it drawn there, it looks like they're connected to each other.
Oh, okay.
And then it doesn't leave any room for anything else. So really, it should be two CH3s connected to something else.
Why does it have to be two CH3s?
It doesn't have to, but it's the most likely choice.
So there should be connected to two CH3s. So there's CH3 is next to it.
Connected to something.
So that means the CH3
So, like,
could be on there.
Let's show you.
But you can't be connected.
Right, so you have two CH3s that are connected to a C in the middle. These two are indistinguishable, so that makes a group of 6.
But then there's one hydrogen.
Right, so now you got a CH group also. So now you got like pieces. You got a CH2, you got a CH. You got two CH3s, and then you got a bromine. Well, that's now the challenge. You have to start piecing this thing together. So you've got this group of 6 is a double. What does that tell you about the two CH3s?
That is like next to these two is
So
Adjacent to them?
adjacent is what? If it's a doublet, how many hydrogens are adjacent? Right. So that means that the CH3s have to be next to a carbon from
Oh, that's what we see CH.
right.
And then there's CH3 right here.
Yeah. So maybe that's just CH right
And then the CH2 would have to go up here.
there. Okay, try that.
That works.
Does it?
Because it's adjacent.
Yep.
And then you can put it one in here.
Hey,
Yeah, you can. 'Cause
how many bonds is carbon?
4,
How many bonds is that carbon?
3.
Does it? Carbon.
How could it be CH3s and the double bond?
Oh, 4, and the hydrogen is 1. So, okay.
So where is there still space open? Where do you see that there needs to be a double bond?
I don't know. Well, in order for a carbon to have sex,
Not necessarily.
I mean, I guess they're gonna have to form
Wait, but what if we put it on the hydrogen?
How many bonds do you have?
Only 1. But, okay. Okay, this is complicated. If the one goes here, here, or here. So this is, these each could get 1, and this could get 1. So only this one. Wow, I turned myself in it. Okay.
How's it going over here? Everybody's quiet.
We got, yeah,
Okay.
That means that
Great.
there's 9 plus That's the
Yeah. So is that the final
No,
structure?
Okay, this is the formula.
So you're kind of checking it to make sure it all fits.
And then there's a C up here. There's C, H,
Ah.
A, and then bromine right here. That's how it's done. Okay. This is
really thinking way too much into it.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, right. No. Only going to have it here.
It's like,
Why are you moving? Oh, I have 2 states. Yeah, I like that. Oh, I think it's easy. Oh, I can't.
Now, why don't you have it? Because you gotta have two CH3s.
How many bonds is there?
Oh, shoot.
So why did you come up with that?
Wait.
All right, this is a good example. So you all have you both have the right pieces,
But she has like,
but they're connected in different ways, which means they're going to have different types of splitting.
Wait, does this make sense? This is this.
Yes.
Right?
So why doesn't, so you two are right, but can you explain why this doesn't?
or not 900.
Because, okay, you see under CH3 here? You see, well, hold on. CH in the middle.
So here's the rate.
Okay,
But no, this is an
But
important.
because
So,
one carbon needs to have one H,
yeah,
but then still have 9 splits, I guess, like 9.
Should I have that?
8, yeah,
8 next to it.
and then with the one with the.
No.
But this is an important part, because once you get those pieces, you have to decide how am I going to put those together. And these are two legitimate ways of putting it together, but only one is right. So you have to be able to.
Oh, the CH was next to this one.
So here's a simpler thing. Yes, all of that is true, but here's a simpler thing. In order to have a group of 6, that means you need 2 CH3s that are in the same chemical environment.
Oh.
These two are not. This one is closer to the bromine, and this one is farther away from the bromine. So we would expect to get 2 separate CH3 peaks with this, rather than 1 6. So you have to put those in an arrangement where they are chemically equivalent. They are in the same place.
So that means they have to be.
So if you look at another structure like this one, these two will be indistinguishable from each other because they're both just the same carbon. Like if you imagine just thinking of one of those hydrogens and flipping this all around, you would be able to pick that one back out. So that's an example of 6. So we can also look at the splitting. For instance, this CH2 group. Here, it's a doublet, which means that you have one neighbor. But in your structure, the CH2 has 1, 2, 3, 4 neighbors, which means it's split into 5.
Like for each has one,
Hydrogen.
one, 2, 3, 4, 5, 6, 7, 8.
Yeah.
8.
That's right. So this is, you get
9
9
neighbors.
for 8 degree.
Got it. Neighbors.
No, not about neighbors, but what else? That it's a carbon attachment to it.
How do you form a structure that has no neighbors?
No neighbors? Well, various ways. Like you could have. Right, you got something like that, so that those hydrogens now have no neighbors.
And you can just do that for like.
Well, there would be other stuff here, but I'm just saying that could be a piece of it that would be.
That's because the C is a double
No,
bond.
because
Right.
it doesn't have a hydrogen. Only thing that shows up on this piece.
You could have like a CH2 that had an O on either side of it, and then some other stuff that would not have any neighbors because it would be spaced out by those O's.
Can I ask you something? Okay, apart from knowing that a doublet, doublet, triplet, or et cetera. So
Yeah.
apart from knowing that these two pieces or anything else that I should know.
So that means, and that tells you how many neighboring hydrogens you have.
Okay, so the doublet was one adjacent, and then that's all.
That's all you
Yeah.
can learn. Okay.
But is
So we're almost out of time. But Wednesday, the lab Wednesday, we're making soap and detergent, and there's some very big lab. But there's a lot of downtime because it has to cook for a while. So during that downtime, bring these back with what you've done on them, and there will be time to answer questions. Yeah.
yeah,
Yeah. So you got your different pieces, right? You can't have a double bond oxygen because there's too many bonds with that carbon. In fact, all your carbons have two bonds the way you got it right now. So look at your split. What's the splitting of that CH3? It's a singlet. What does that mean? No neighbors.
Each other.
So how could you make it not connected to the CH2? Like still a part of the molecule, but not connected to the CH2.
But the CH,
Oxygen.
so that's how you can, because then there's CH, and it's.
Yeah.
But I need to know why
Because I can't add it in well.
So now you got the CH2 splitting each other, the triplets, and then the CH3 is not split.
In between here, you need a C.
Oh,
Yeah.
so the two CH3s have.
Yeah. The CH and then the CH2. Like,
So they have to be adjacent.
and then the CH2 has to be adjacent to the adjacent. Or we have you all or we have
That's right when we walk in then.
On Wednesday, yeah, we'll do it right away, and then we'll handle that.
So this is. This is.